Hello everyone. Alright, today we're going to do two new things. The first one is putting types into classes. So how can we actually define what class a type should be in? So let's give an example here. So there's a class called show with a capital S, and in it there's a function that says there's a function from any type A into string as long as A is in the show class. So as long as this type A is in the show class, there is this show function. Now, show function is just a standard function we're going to use for write. You've probably seen it in error messages saying no type defined for show, and that's what this means. There's just a function, a generic function. If we give it a value and show it, it's going to return a string. Okay. There's a complementary function called read, which goes from a string into something of type A, so it's going to read something of this type, and it's for any type that's in the read class, which is notice there's the capital R and that's a small r. The class here is a capital and the small is the function. Okay? And if we want a default implementation of show and read, all we're going to do is here's our definition of a binary search tree with key type K and value type V. All we need to do is we're going to put deriving show and read. So that defines the function little show and defines the function little read. And in particular, it lets us read and write things in GHCI. So it lets us as soon as we do this, we can then write out things of type BS tree K and V. Right? If we didn't do this, we couldn't write out a tree because it would just give me an error. Just give us an error. So most of the predefined types, except for functions, are in both show and read. So if you try and print a function, you get an error. And the error will say it cannot print it because it's not in the show class if you try a function. And similarly, we've seen this before. EQ as a class contains the functions not equals and equals. Right, so that's the EQ class. But we can actually we could do deriving EQ and it would derive a default value of equal. But for binary search trees, you probably don't want to do that. So what you'd like to do is you'd like to say that there's the same set of key value pairs. So what we can do is we could show that we could say that BS tree K of V, this one, is an instance of the EQ class. That's what that says. But it's only an instance of it if K and V are in the EQ class, right? So this one says that BS tree KV is an instance of the EQ class as long as K is an instance of the EQ class and V is an instance of the EQ class. And when we do this, we then have to give a definition for equals. So this is actually just a standard definition for equals equals. So we're saying T1, binary search tree T1 equals binary search tree T2 if when you convert T1 to a list, you get the same values as T2 as a list. Now, this is an interesting one. Because of lazy evaluation, we only do as little of the tree as possible in order to check that if they're not equal. So it only checks the whole trees if they're equal. Otherwise, it's going to fail as quickly as it can. Okay, that's because of lazy evaluation. If you try and write a function that works like that for equality of binary search trees, in other languages, it's actually very difficult to write a function that basically enumerates the values and just returns, and if any are different, it's going to fail. Okay, so in Haskell it's easy to do that. In most languages it's actually hard because this one only does as little of the two list as it needs to in order to work out whether they're equal or not. Okay, and here's another function that's interesting. This is sort of a more tricky case. So it turns out that fmap is a generalization of map defined for anything in the functor class. Right, so there's a functor class, right? And functor class has this function called fmap, which takes something of A to T, and here it's going to return, so it's a function like map, so it's a generalization for map, but now it's going to be used for the binary search trees as well as for lists. So now what we're going to do is we're going to say it takes something of BST, given the function from A to B, and a BST type with key type K and A type A. it's going to return a binary search tree with key type K and value type B. Okay, and here's fmap, and fmap is defined as the empty list gives the empty list. Otherwise, fmap applying to the node returns a new node where we're applying it to both the head and the tail. Remember, this is a lot like map, except now map was for lists, but this is for binary search trees. Okay, but fmap is also defined for lists. So if any function you have for any map that you want to apply to the values of a tree, you can now use fmap, and it can work just as same for lists. And notice here, it's funny what we've written here is because we're not applying it to, we're only applying it to the values, not to the keys. So it turns out it doesn't make sense because it messes up the whole point of a binary search tree where the keys have to be ordered if you can just change them arbitrarily. The other part we're doing today is we're doing input-output. So it turns out that IO of t is a type, so it's a parameterized type that does input and output. And there are functions we're going to look at. We're going to look at put character, put string with an end of line character. So they're the sort of functions that we're going to do for output. And we're going to look at get character and get a line. So this one reads a character, and this one gets a line either from the terminal or from a string. Okay, and there's this funny syntax we're going to use. So here's the idea here: is it's going to evaluate A1, then evaluate A2 in turn. And A1's going to evaluate to V1. This might be like read a line, and that's going to be V1's going to get the value of the line. It might be, get line, and this one here is going to be a line. It might say get character, and this is going to be a character. Okay, and then we're going to return some function. It's a function typically of all of these values. This might be a function of all the values that we've read. And this one, if you only don't want to actually, if we want to put the character or put it, you might not want to return anything, so this might be optional. Okay, and eventually it returns the value of f of f1 to fn. So we can imagine this, read a few lines, do something with them, convert them into a number, add them, do something. Okay. So instead of, you could actually call another function that has a return here. So this does, so it says return here, we don't have to have return at the end. If you call another function here, it will actually just evaluate to the value of that function. We're going to see, if you look at ioadder.hs, you'll see lots of examples of this. So here's a little bit more detail of what's going on. So IO of t is a type for input and output. In some sense, so one of the ways of thinking about this is IO of t is a function from the state of the world into a pair of t and the state of the world. So that's what IO of t. So IO of t you can think of as a function. So it's a function that takes the state of the world, returns a value, and a new state of the world. Okay. So now let's look at this same function again. So you have do of v1 is a1, vn if an. So each ai here has to be of type io of ti for some type t of I. Okay, so each one of these is going to take a world and returns a value and a new world. And this vi has to be of type ti. So vi is going to get the value that this output, that ai returns. So this one here is going to correspond to the value that's going to be put. Okay, so what's going here? So there's an outside world. There might be the state of the whole world in here that comes into A1. A1 updates it, gets a new state of the world, and it outputs a value to V1. So then A2 takes that state of the world and gives its value to V2, etc. And eventually AN gets the state of the world, returns that to VN, and this one here gets a new state of the world, which is then passed on to the return. Okay, we'll have a look at that again, what's going on there in more detail in class. Okay, the type of the expression is IO of the type of this. So whatever type of f of v1 to vn is, that's the type of this expression. Okay, and we can actually, in this expression, in these do statements, we can also define lets. This is the local expression. With this, it's not an IO something. This is just an expression. We can add numbers, append things, do all sorts of things we might want to do. Alright, so what we're going to do is to play with this in class, but hopefully that's given you some sort of introduction to where we're going here. So have a look at IOAdder and IOAdder2.hs, and there's been lots of examples of doing this.